Hello, my name is Hannah Fowler, and I'm here with Decking Engineering to present the Critical Design Report for the Tarleton Engineering Office Suite design. I am a civil engineering student, as well as the team lead and the geotechnical lead for this project. Here is my team, Noah Easom, Jonathan Mink, and Blake Donahue. They will tell you a little bit more about themselves when they present their parts of the project. The goal of this project is to design the foundation, the parking lot, the runoff management system, and the ground remediation for the new engineering building at Tarleton State University. This project is to design the foundation, the parking lot, the runoff management system, and the ground remediation for the new engineering building at Tarleton State University. The project will be presented in the same order as each section was just listed. I will be going first with the geotechnical component. The goal of the geotechnical component is to design the foundation for the office suite. Some of the design deliverables are as shown: the bearing capacity, the settlement, all of the drawings and details, as well as the general notes, inspection plan, and cost estimate. Here are some of the design considerations, such as the International Building Code, the building code requirements for structural concrete, the bridge design specifications, the structural loads, and the bearing capacity of the soil. All of the structural information used to determine the type of foundation, as well as the dimensions of the foundations, was provided by K16 Consulting. The preliminary design considerations for the foundations was a pile foundation and a shallow foundation. Both were acceptable, but the shallow foundation is more economical, more cost-effective, and needed less material, so it was determined that a shallow foundation was the best option. For a more sustainable design, a shallow foundation with recycled aggregate was also considered, but due to time constraints and the lack of research on recycled concrete, it was decided it was best to use a more traditional concrete for the shallow foundation. The following shows the shallow foundation design. First, the settlement was calculated to determine that a shallow foundation is acceptable. Here shows the summary of the total settlement calculation. The total settlement is less than an inch, which means that it is safe to use a shallow foundation. Each footing was sized based on the loads and the moments on each column. This table shows a summary of the footing sizes that are used, as well as the reinforcement, bar numbers, the quantity, and the bar spacing. This image shows the footing schedule and the basic drawing for each footing. Here is the location details for each footing, along with the size and the symbols legend. Here's the cost estimate for the foundation design. This cost includes labor, and the total cost estimate ended up being around $20,200. I will now hand it over to Jonathan Mink to discuss the transportation section of the design. Thank you.
Thanks, Hannah. My name is Jonathan Mink, and I'm a civil engineering major at Tarleton State University, and I'll be going over the transportation component portion of the project. The design objective is to have a parking lot for the new engineering building at Tarleton State University for the new engineering building. The design deliverables will be delivering a pavement thickness for the new parking lot, along with a joint and steel design. Detailed drawings will be shown later on the slides, along with the custom concrete mix for the parking lot and a cost estimate. The design considerations will accommodate about 45 total parking spots, with 2 handicap parking spots located near the front of the building. A 6-inch curb will go around the parking lot to help manage stormwater runoff with a 2% slope for the parking lot. The entire area of the parking lot will be a little over 26,000 square feet, with a 4-foot sidewalk running the length of the engineering building. There'll be 2 semicircles that will provide a green sustainable design that will help reduce total cost because it will require less concrete and steel. And a second option for flexible pavement will also be discussed here in the next slide. So flexible pavement versus reinforced concrete design. Because of the high traffic of Tarleton, reinforced concrete is preferred method because flexible pavement has too much wear and tear over the years, so it will require more flex sealing and more striping and more maintenance with potholes and other cracking issues. So a reinforced concrete design for 20 years will be recommended for the design of the new engineering building. The design of the subgrade. So for the modulus of subgrade reaction, the modulus of subgrade reaction is used is found using the California bearing ratio. From the boring logs, a poorly graded sand and soil properties is found that the K value is for a 6-inch granular sub-aggregate base, and it'll be 260 pounds per cubic inch. For the design for the thickness of the reinforced concrete parking lot, the original design thickness from the K value of 260 is that the design thickness of the reinforced concrete parking lot will be about 3.5 inches. But because we're doing a reinforced concrete design, the minimum thickness will have to be 5 inches. Having a joint design is essential for the concrete parking lot because it will prevent cracks from occurring, and it will help us use dowels in the design. For the area of steel, the area of steel calculation is shown below. The total area of steel that is going to be needed in the design of the parking lot will be 0.014 cubic inches. Here's the steel design for the parking lot. It shows the dowels and the tie bars and the way that the rebar will be shown. And it also shows the 2 semicircles that will help reduce the need for extra steel and extra concrete. For the concrete mix design, the first thing we need to do in the concrete mix design is to calculate the total amount of concrete needed. We'll need just at under 390 yards of concrete for the entire parking lot. The recommended air content is going to be used from the manufacturer specifications of 0.15 fluid ounces per 1% air per 100 pounds of cement. The design of the mix calculations are shown here below. It shows the water volume, cement volume, air, coarse aggregates, and along with the fine aggregate. And the next slide, we'll talk about how we use the modified water design. The water correction is shown here in the calculation from 240 to 115.13 pounds. And the aggregate dry mass water percentage is also shown here that we will need a total of 124.87 pounds of water per yard of concrete. The summed up design of the PCC concrete design is that it will be a 20-year thickness with 12.5-foot spacing between joints. The area of distributed steel will be 0.014 square inches with a tie bar size of 1/2 inch by 24 inch. The total area is just a little over 26,000 square feet with a 5-inch slab, needing 389 yards of concrete to finish. We'll be using a manufacturer specification of 0.15 fluid ounces per 1% air per 100 pounds of cement and no larger than coarse aggregate of 1.5-inch nominal size. The batch ingredients for 1 cubic yard of concrete is shown here in the table below with the water, cement, coarse aggregate, and fine aggregate along with the admixture. The design of the parking lot is shown here with the aerial view showing how the parking lot should look with the stripes and both semicircles. The design of the parking lot also shows the curb design and the saw cut of the dowel designs here in both figures. The design cost estimate came in right at under $100,000. It includes the labor and the material price for the parking lot. And I'll be handing it off to Blake Donahue to talk about the water resources component of the project. Thank you.
Thank you, Jonathan. I'm Blake Donahue. I'm an environmental engineering student, and I'm Ducking Engineering's water resources lead. This component of the project is tasked with designing a stormwater management system for the proposed development, with the consideration of best management practices. The deliverables within this section included the development of a runoff control and treatment drain, the sizing of system components, drawings and specifications, as well as a cost estimate for the recommended design. Criteria used in these designs were specified in TxDOT's hydraulic design manual and the Cities of Houston's stormwater management requirements. A design alternative using best management practices followed the Harris County Low Impact Development and Green Infrastructure Design criteria for stormwater management. This proposed development features an office suite, parking lot, and sidewalks. These will introduce impervious surfaces to nearly 1/3 of the site, thereby increasing the runoff. A storm sewer lies under Lillian Avenue along the downslope perimeter of this site. The site was partitioned into parcels in order to better quantify the peak flows impacting components within each one. This first design features a curb inlet to capture the runoff from the first parcel, and the remaining parcels will be drained by graded inlets. The system directs flow downstream through conduits into the existing stormwater utility under Lillian Lane. An earthen berm partitions the parcels. A slot in this berm conveys carryover discharge for further capture downhill. The second design features a rain garden and planter box, which were selected for based upon their ease of implementation and minimization of their costs, including maintenance. The runoff control and treatment train for this alternative directs runoff from impermeable surfaces to components that allow for detention and the treatment of water quality. The recommended design was selected based upon projected costs and timeframes of construction. Since no local regulations require the detention or treatment of runoff water quality, these design criteria were given lesser weight. This resulted in a decision to recommend the traditional stormwater runoff design. This design will utilize the existing storm sewer adjacent to the site and will be constructed with prefabricated components. This design was conducted through peak flow calculations in order to size the inlets following TxDOT's equations. The conduits were sized in order to convey the peak flows, and their slopes were determined through applications of the Manning's equations. A 10-foot curb inlet was selected. The carryover discharge resulting from this inlet size was calculated to be well within the limits defined by TxDOT. The smallest commercially available graded inlet and catch basin was selected. The smallest available concrete pipes were chosen and placed at a 2% grade to match the average slope of the site. This cost estimate includes a silt fence, inlet covers to protect against sediment pollution. Since calculations assume that the undeveloped areas of the site were covered in grass, this cost also includes the amount of sod needed for the design. Thank you. I'll hand it over to Noah.
Hi, my name is Noah Easom, and I'm the environmental lead to this project. So Tarleton State University has been recommended to reduce the lead concentration levels from 800 milligrams per kilogram to below 400 milligrams per kilogram before any further action regarding construction can begin on the office suite. The design deliverables given will be the design criteria, primary design schematic, preliminary lab results for design, and a cost estimation. So based off our phase 1 site assessment, we found that the proposed construction site was near a former lead smeltering factory that had been demolished and inactive for multiple years prior. The evidence shown that these particles were released directly into the air as suspended particles and were carried into the proposed construction site by wind and rain. The phase 2 site assessment was completed in December of 2020 and shown that the average particle sizes of lead were 200 micrometers in size and mostly within the first 6 inches of topsoil. According to our boring logs, we saw that the soil does not begin to become saturated until 21 feet in depth, which means most in situ processes are almost impossible without having to saturate the clays and other soils with electrolyte and chemical solutions, which is going to be very detrimental for the environment. Up next will be our selection of design process. Design number 1 involves an electrochemical process where we would excavate the untreated soil, transport it to our remediation site, where it would go into a pretreatment of 5% KCl and acetic acid. From there, the solution will be transferred to our agitator table, where the lead can be collected, and then the clean soil can be moved over to our electrokinetic reactor with iron and aluminum electrodes. And from there, the contaminated solution can be moved over to our lead collection chamber and be sent to our landfill, while the clean soil can be sent back to the remediation site to be mixed and recompacted for construction. Design option 2 is very similar to option 1, except it is just the chemical wash portion. So we would take the untreated soil and transport it to our remedial site where the pretreatment of 5% KCl and acetic acid can be applied, which will run through the agitator table. Then the contaminated solution be collected in our lead collection chamber where it can be sent to our landfill, and then the clean soil can be transported back to our remediation site in order to be recompacted for further construction. Our design matrix criteria was given based off of a rating of 1 or 2, with 2 being superior. And since our client stated the percent reduction had the highest priority of all of the design criteria, it got a 60% major rate. And based off of the results of this, the electrochemical remediation got a total score of 1.55 versus 1.30 for the chemical wash remediation. Because of that, we're going to recommend and show the design for an electrochemical remediation. Up next will be our electrochemical design analysis based off of our laboratory studies. So for the chemical wash portion of this process, we compared 5% acetic acid in KCl solution with 5% acetic acid and 10% KCl solution. As you can see here on the table, the highest average percentage reduction is 58.5% with the 5% acetic acid and KCl solutions. Here's a graphical representation based off the different pulp densities, of which the 3% pulp density had the highest removal with the 5% acetic acid and KCl solution. Up next would be the efficiency of using aluminum and iron electrodes after our chemical wash for the electrokinetic reactor, of which we compared running 2 amps and 7 amps in our electrokinetic batch. Based off of this, we saw that the 2 amps had the highest removal efficiency of 97.3%. And this is with the aluminum and iron electrodes being spaced within 10-foot intervals based off the EPA guidelines. Here's a graphical representation of these electrode combinations based on different time frames. Based off of this, Ducking Engineering recommends that Tarleton State proceed with the electrochemical remediation design, as it will have the highest chance of success with the reduction of lead levels below 400 milligrams per kilogram, with a 97.3% reduction, compared to only 58.5% with just the soil wash. Now, it should be noted that these are laboratory results, and they should expect to yield a certain percentage of error when applied to much larger quantities of soil, which could possibly put option 2 not at risk of doing the 50% reduction recommended by the EPA. Up next is the electrochemical process cost estimate. So at the base off of this, the electrokinetic process and soil washing process will be performed by Ducking Engineering themselves, which allows us to lump in the cost of labor and design cost into this total estimate, which is seen to be $3.3 million in costs. More details can be found in the Appendix A3.
An uncertainty analysis was performed for the geotechnical and water resources components of this project. Error may be present in variables used in design calculations. Because of this, these variances of the parameters were applied to design calculations to evaluate the recommended designs. The value for the intensity of rainfall for this design storm was sourced from NOAA Atlas 14. This value is estimated from a partial duration series, which may introduce error due to variability in the sites that collect the data. Because climate change may alter precipitation trends, this estimated value may vary over the course of the design's life cycle. The value for the runoff coefficients within the rational method may have variances of 7.5%. Peak discharge calculations were evaluated, and they did not result in a change to the design's recommendations. The roughness coefficients selected within the modified Manning's equations may vary by 20%. With this variance, along with the variances of the calculated peak discharge were applied to design calculations, they did not affect the recommended components. The excess bypass flow from the curb inlet did remain within the limits.
To account for any uncertainties in the foundation design, a factor of safety was implemented. The factor of safety is included in the design to ensure the safety of the public. The factor of safety used in this foundation design is 3. This value is advised by a mentor, so I decided it was the best value to use to ensure an adequate design. The factor of safety was applied to the ultimate compressive strength and used to determine the allowable compressive strength. This directly affected the size of the footings required, making them larger and therefore safer. Next, we have the sustainability criteria. This table only shows a small portion of the barriers preventing us from implementing a more sustainable design. A full list of barriers can be found in the sustainability section of the design report. Here's a timeline for the construction, showing each of the different sections and approximately how long they'll take, as well as their predecessors. The bottom image shows the Gantt chart for the construction. Each of the numbers on the squares correlate directly with the numbers associated with a task. The red tasks are the critical tasks that must be completed on time. The construction process is estimated to take 147 days, not including weekends and holidays. Finally is our responsibility matrix. Here are some of the tasks that were completed outside of our individual design sections. Each person was either responsible or classified as contributing to a particular task. This does not mean that the other team members did not help with these items. It just means they were not responsible, but everybody contributed equally. Here's a list of references used throughout the report. We appreciate you listening to us patiently, and if you have any questions, we would love to hear them. Thank you.